Hi friends, welcome on board for another project. This time I decided to design this beautiful switching power supply board. Let me show you the board from different angles. So here's the AC input, universal in the range of 85 to 260 volts. And here's the DC output from these two pads. 12 volts and 3 amps maximum continuous. It means 36 watts of power maximum continuous. As usual, I designed the schematic and PCB using Altium Designer, and I have uploaded the PCB files in my Altium 365 cloud space. To download the files, first you should register on the Altium 365 cloud space. So simply follow this link and register on the Altium 365 website. Then simply follow this link and download all of the files for free. Let me explain the board. From here is the AC input from these two pads. It comes through this fuse. For protection, of course, a varistor or MOV for protection, especially high voltage transients. This is an NTC to limit the inrush current, and X to rate the capacitor for noise reduction, especially high frequency noises, a command mode choke for noise reduction. All of these components have a significant effect to pass the conducted emission test. You can make your own research about the conducted emission test. This is the bridge rectifier to convert the AC to DC, and of course this fat guy is the main capacitor for ripple reduction, 82 microfarad and 450 volts. This is the Mosfet to switch the primary of the transformer, and these three components belong to the RCD snubber to reduce the ringing and spikes on the primary of the transformer for the main purpose of protecting this Mosfet. The RCD snubber also has an effect to pass the conducted emission test, but the main purpose is to protect the Mosfet. This is the auxiliary winding of the transformer to supply the controller, and here is the controller. These components are to stabilize the voltage of the auxiliary winding and to supply the controller. So, an optocoupler to provide a galvanically isolated path for the controller to sense the output voltage and regulate the output voltage. Of course, a Y capacitor. At the output, a Schottky diode to convert the high frequency AC to DC, and these capacitors and this inductor to reduce the noise, an LC filter. This is a dummy load to stabilize the output. Of course, an LED to indicate there is a voltage at the output, and this potentiometer to precisely adjust the output voltage on 12 volts. This is the back side. Almost a solid ground plane to reduce the impedance and length of the ground path. You know the effect better. The minimum effect is to reduce the noise and also to reduce the EMI. This small component is the shunt regulator SOT23 package. You can see the isolated path areas or creepage areas at the below the Y capacitor, below the transformer, below the optocoupler, here on the primary, at the input. I will explain more when I explain the schematic and PCB. So let's go to the next step. Alright, here is the home page of my Altium 365 cloud space. You remember all of these previous projects, isn't it? By the way, this is the latest one which I will talk about, but wait a minute, you can create your own space for free, the same as me. Just follow this link in my YouTube video description and register on the Altium 365 website. Then come here and upload your PCB project and share it with your friends and your colleagues. But you may ask, what's the catch? What's in it for me? The main benefit of this Altium 365 is, although it has many other features, when you're working on a PCB project, and especially if that PCB project is complex and you're working in a team, for example, a team member designs the power supply, another team member designs the RF part, Wi-Fi, Bluetooth, and similar, another team member designs the digital circuits, microcontroller, FPGA, DDR RAM, and etc. If you communicate traditionally using email, of course, you will live in a mess of PCB files, communications, feedbacks, edits. This is prone to error, miscommunication, and misunderstanding. This process causes delay, and delay means waste of time and waste of money, a loss for the company. But here, all of you are connected through the Altium 365 cloud platform. If I, as a digital designer, for example, apply an edit or feedback for the power supply designer, he will receive that feedback live on the cloud. And he can also communicate with me and apply an edit, for example, change a capacitor, a decoupling capacitor for me. If you have worked on a complex project, you can feel pretty well how much this feature is beneficial. By the way, this is the latest project. So this is the schematic document. This one is the PCB layout, and this one is a 3D view of the PCB board. Let me start to explain the schematic from this upper edge. Here is the AC input. It goes through this fuse for protection, of course. R2 is a varistor to protect the circuit against high voltage transients. C1 is an X2 rated capacitor to reduce the noise. R1 is to limit the inrush current, the startup inrush. T1 is a common mode choke, bridge rectifier, and C2 is the main capacitor for ripple reduction. Use a high quality capacitor for C2, otherwise it might dry out too soon. It should work for at least 7 or 8 years minimum. Look at here, when I put the cursor on the net, this Altium 365 highlights the net on all parts of the circuit. This feature is especially useful when you want to present your schematic to the team in a big 4K or HD TV. By the way, this high voltage DC line goes through the primary of the transformer, and other side of the primary is connected to this Mosfet. This Mosfet switches the primary with the frequency of 65 kHz. This RCD snubber is to protect the Mosfet. Although it has effect, it could have a good effect to reduce the EMI and to pass the conducted emission test. These two resistors are to prepare the startup current for the controller. I think for this controller, the startup current is around 30 or 40 microamps. That's why the value of these two resistors are high, and we don't need to use a high power resistor here. After the startup process, this auxiliary winding of the transformer will supply the controller. So this D3 is to rectify the AC voltage. These two components build an RC filter to reduce the noise, and this D5 ensures that the voltage on the VCC line of the controller does not go higher than 24 volts, because when you connect the power supply to the high voltage mains, for example 240, 250, and you draw the maximum current, the voltage on the auxiliary winding also increases. However, the current draw from the auxiliary winding and the controller is low. That's why a cheap ordinary Zener diode works here for the best and keeps the voltage well below 24. Otherwise, higher voltage might turn off the controller and activate its internal protection mode. This R3 is recommended by the datasheet. If I remember correctly, is to set the frequency on 65 kHz. This capacitor, this C10 and C11 in parallel, they build a lower ESR capacitor, okay? Also to reduce the high frequency noise and to enhance the lifetime of this C11 capacitor, because this capacitor also might dry out too soon. So this C10 has two good purposes here: reducing the high frequency noises and also to reduce the total ESR of both capacitors. Let me zoom out the circuit. This optocoupler provides a galvanically isolated path for the controller to sense the output voltage and regulate the output. At the output, we have this Schottky diode to rectify the high frequency AC voltage, and this pi filter is to reduce the noise. Of course, this LED to indicate that there is a voltage at the output. This is the Y capacitor for protection and also noise reduction, and you can precisely adjust the output voltage using this R19 1K multi-turn potentiometer. I think I covered most of the technical points. If you have a question, just let me know in the comments section. I go to the PCB. Let me enable the layers. For example, disable the top overlay. You see I have followed several PCB design rules to draw this PCB. If I disable the top layer. So this technique, using this solid ground plane for the bottom layer, will reduce the length and impedance of the ground path. The result is lower noise and lower EMI for the output. I did the same thing for the input. If I enable the top layer, you will see I have followed the same rule for the top also. Use some wires to reduce the length of the ground. And here at the output, there is no loop at the output side. If I enable the top overlay, the loop from the Schottky diode to the first capacitor is pretty small. I mean from here. The start of the Schottky diode goes through this capacitor to the ground of the transformer. This loop should be as small as possible. Also, the feedback line should be away from the switching parts like this inductor or the Schottky diode. Also, the feedback line should exactly sense the output, just here, as I put the feedback from here. The RCD snubber should be as close as possible to the transformer. The same thing should be followed for the drain pin of the Mosfet here. So drain pin should be as close as possible to the primary of the transformer, because here we have wild switching currents, and if you use a longer path to connect these two pins, this is a good candidate for more than enough radiated emission. So this line will act as an antenna. That's why we should keep it as short as possible. You can see the isolation gaps and creepage areas. I put here below the transformer, here at the primary near the drain pin of the Mosfet, here at the input. This is to follow the high voltage IPC standards. So, and also here, okay, below the optocoupler. I think I covered all of the points. By the way, as I said, if you have any question, just let me know in the comments. Alright, I have prepared this picture to show you what type of ferrite core and bobbin you should buy. Also, the winding pattern of the transformer. If you look at the left picture, you should buy this ferrite core, EFD25, and this bobbin. You can find exactly the same ferrite core and bobbin on the market, so no problem with that. The winding pattern also is pretty obvious. For example, these two pins is the primary winding, these two auxiliary winding, and you can find the specifications of the secondary winding on the right side. For example, the primary winding is made of 56/10 of 0.4 mm of magnet wire. This is the gap size, mathematical calculation, and you should play with the gap size till you reach this inductance in the primary. My assumption is that you know how to wind the transformer, especially for prototyping you will wind by hand, I think. By the way, don't forget two things. Wrap 2 or 3 layers of transformer tape on the primary after you finish the primary. Also use heat shrink on the wire ends of the primary because high voltage isolation is important in such a small transformer. By the way, that's it for transformer. Let's go to the next step. Alright, welcome to the table again. I have prepared the setup to test the power supply board. Here is the AC input, and this side is the DC output. You can see the LED lights up, and the output is connected to this DC load. The output voltage is 12.027. So for the first test, I will apply the maximum load, which is 3 amps, to the output, and we will examine this number to see how good or how tight is the regulation. So I set 3 amps on the DC load, and I will turn on the output. 1, 2, 3. So just 4 or 5 millivolts voltage drop at the maximum load. A big thumbs up for this power supply indeed. For the next test, I will examine the spikes and ringing on the primary of the transformer. Alright, I have connected the oscilloscope probe, I mean channel 1, to the drain of the Mosfet and the ground lead of the probe to the input ground. For this purpose, you should either use a high voltage differential probe or power your board using an isolation transformer. The board, I mean your device on the test. In my case, I don't have a differential probe, so I use an isolation transformer. And by the way, this is the waveform when there is no load at the output. So it says the peak-to-peak voltage in this condition is 470 volts. But what happens when I apply the maximum load, which is 3 amps, to the output? 1, 2, 3. And there we go. This is the waveform. Now it says the maximum peak-to-peak voltage is 510 volts. Maximum, or 500. This is well below the maximum drain source of the Mosfet, which is 650 volts. So the snubber does the job and it is pretty acceptable, but it is better that we don't see any sharp edges on this ringing here. It is pretty important to pass the conducted emission and EMI tests. So let me play with the volts division knob and examine this ringing here. And as you see, I don't see any special ringing, sharp edges on this ringing. You may ask why the waveform is like this. This is the jitter feature of the controller and is used to reduce the EMI. It's not a problem. So I don't see any sharp edges on this waveform. So the snubber does the job perfectly, and this power supply is a really good design. So I hope you like this project. Don't forget to share and subscribe. We will do something else in the next video.